So far we've just looked at individual numbers, right? We took a single number, talked about factors, multiples, prime factorizations, those kinds of things. Well, what if we kind of take the next step up and look at two numbers? For example, I got these two numbers here, 56 and 84. What is their greatest common factor? Right? I'm looking for the biggest number that goes into both of them. Well, I mean, we could try just kind of going brute force. 2 goes into both, 56 and 84. So that is a common factor. Just kind of working my way up. 3 doesn't go into either one. Yeah, but 4 goes into both of them. So it's not 2, right? Maybe 4. I don't know. There's a lot of numbers we potentially have to check if we're going to do it this way. It's not too bad when the numbers are small. But even when they get up into just the mid 3 digits, okay, that's an awful lot of work. Well, fortunately, we don't have to do that. We have an algorithm we can use. An algorithm, fancy term. It's just a sequence of steps. It's a procedure. All right, so here's how it works. I'm going to start by finding the prime factorizations of the two numbers using either of the methods we talked about in the last lecture. 56 is 2 to the third times 7. 42 is 2 squared times 3 times 7. Step number 2, I'm going to list the factors that they have in common. Now, when they both have a 2 and they both have a 7, they don't both have a 3, so that doesn't make the list. Step 3, I'm going to give each number the smallest exponent. Well, it's the same with the 7s. It's kind of an implicit 1, or it doesn't have one if you really like to think of it that way. With the 2s, there's a 3 and a 2. The smallest one is the 2, so that's what I'm going to use. 2 squared and 7. And that's all I need. Now I can get my final answer. I'm just going to multiply those numbers together. 2 squared times 7 is 28. That's the greatest common factor of 56 and 84. Okay, well, how about if we want to go the other way? Right? How about multiples? Well, because multiples are always bigger, there is no greatest one. We can keep multiplying by bigger and bigger numbers and have bigger and bigger multiples. So with multiples, what we're going to want is the least common multiple, the smallest number that is a multiple of both of these. And again, I mean, we could brute force it, but that one, there's no limit to how big the number could be. You really could be here for quite a while. So fortunately, we have another algorithm, and it's very similar to the previous one. Find the prime factorization, starts off the same. Now, the second step is really similar. We're going to list all the factors, right? So I don't just want the ones they have in common. I want kind of the complete list. It's going to be 2, 3, and 7, all three of them. Step 3, I'm going to find the greatest exponents. 3 and 7, again, that's going to be 3 and 7. With the 2, now instead of the 2 squared, I'm going to go with 2 to the third. And it ends the same way. Multiply these numbers together. 2 cubed times 3 times 7 is 168. And that's it. That's the least common multiple of 56 and 84. So there's a really cool relationship between these things here. Right, so but the first thing, I want to show my little abbreviations here, right? Writing out those names, greatest common factor, least common multiple, they're a little long, gets a little old. So we usually abbreviate them to GCF and LCM. So the greatest common factor of 56 and 84, that's 28. The least common multiple, we found out that was 168. And here's what I want you to do. Multiply those two numbers together. Right? The greatest common factor times the least common multiple is 4,704. Now, do the same thing with the original numbers. 56 times 84 is also 4,704. That is not a coincidence. The greatest common factor times the least common multiple will always be the product of the two original numbers. And that's going to give us a nice little shortcut. Finding the greatest common factor wasn't too bad. With the least common multiple, the numbers can get a little big. Right? So here's a little shortcut we can use. Remember what I said. The greatest common factor times the least common multiple equals the product of the two numbers. Well, let's say we've just found the greatest common factor. The smaller one, it's usually a little easier. So I'm going to put 28 in there for the greatest common factor. 4,704 on the right-hand side for the product of the two numbers. But now look what I can do here. If I divide both sides by 28, I get the least common multiple is 4,704 divided by 28, which is just 168. Right? I get that number without having to go through that whole algorithm process. So it's a nice little shortcut. So I got one more example I want us to look at here because it's going to give us kind of an interesting situation. All right, let's say I want to find the greatest common factor of 21 and 16. All right, well, I'm just going to follow our method. The prime factorizations are 3 times 7 for 21 and 2 to the 4th for 16. Now, step 2 says list all the factors that they have in common, but there aren't any. Okay, so what happens? We still got to answer the question. Well, there is an answer. Okay, two natural numbers, they always have the least common multiple, and they always have a greatest common factor. If you find yourself in this situation, remember, 1 is a factor of every number, every natural number. Right? Which means 1 is sitting there patiently waiting for us to pick it, right? In a situation like this. So when you get to step 2 and there are no common factors, my answer would be the greatest common factor is just 1. Okay, so those two algorithms, I mean, they're great and not really hard to implement. I really kind of think the hardest thing about them is that they are so similar, right? Do you go with all of the factors or just the ones they have in common? Do you go with the biggest exponent or the smallest exponent? The way I remember it, remember I mentioned this in an earlier lecture, factors are always smaller and multiples are always bigger. So if you have a choice between picking a big thing or a small thing, factors get the smaller list or the smaller exponent. When you're trying to find the least common multiple, multiples get the bigger list or the bigger exponent. Right? In my head, that's kind of how I remember where to go in steps 2 and 3. Okay, so moving on from natural numbers, right? Natural numbers are great. They were kind of an obvious starting point, right? Because you can do them on your fingers. But it turns out there are some problems. Right? There are some deficiencies. In the next lecture, we're going to look at what that is and look at how we can expand on the natural numbers to a bigger set of numbers called integers that don't have that particular problem.